On some MATLAB software. I didn't write this, I acquired it, I'm sure. But this is a typical MATLAB program which does something. It's a function. And you've seen this kind of notation before. Just like when you write f of x equals 15, x plus 12, the f of x is the output, and then the inputs are on this side. And so my function is called Gersh of a comma no plot. Those are the variables. Capital A, I'm sure that's a matrix. No plot, it must be that sometimes you want the values of the Gershgorin disks, but you don't want to take time to plot them. That's what that option must be. So those are the two inputs. And then the output is G and E. And I don't know what those outputs are yet. G is probably a matrix and E is probably some number. Not sure. Oh, here it is. Suppresses the plot, returns the data in G, and A's eigenvalues lie in E. Okay. So yeah, G comma E. So E is the output that has the eigenvalues, kind of like we do V comma E. So I guess we could check our quiz using this if we want. And is this a fair quiz? I don't know. I mean, one thing that these do for me is they tell me what did you understand from the reading and what did you not understand. So I'll tell you one thing, just my glancing over the quizzes says to me, for the most part, I think we know what we mean by a dominant eigenvalue. First of all, did you guys compute the eigenvalues for the matrix? What'd you guys get? 4 and 1? Okay. I mean, I guess I could... 4 and 2? So you got 4 and 2? Either way, by the dominant eigenvalue, what do I mean? The highest absolute value, that's right. What does that mean? Well, 4 would be the dominant eigenvalue. It's the farthest one from 0, okay? And it turns out that the methods in this section can be used to find that eigenvalue. And one of my jobs today is to kind of explain why that happens, okay, and how that happens, okay. Methods, I saw a lot of people wrote down the power method, and then we have some other nice answers. The inverse power method, the power method, everyone with power method. The power method is the first one listed, and the others are variants off of it. Well, what's the inverse power method? Well, that's one that I'm going to explore with you because that's going to be important for if I want to give this talk next week about what I did. I worked with matrix inverses, okay, in my research.
What's the other one where you take the minus eigenvalue?
Yeah.
Minus the first one.
The shifted power method.
Right.
And then you put them together. Shifted inverse, and that's really what you're going to want to understand if you want to kind of follow what my talk does. Okay, so we will get to those things. What about number 2, the Gershgorin disks? So I am guessing that we had trouble. It seems to me this is a tough topic to explain in a book. They show some pictures which help. Here are some Gershgorin disks, right? So what do I see? Oh, and here are some Gershgorin disks. So what I think is fairly easy is to figure out what the center of a Gershgorin disk is. How do you get the center of a Gershgorin disk? The diagonal entries. So one of the disks is centered at 2 and one centered at -3. Here they are. 2 and -3. And the Gershgorin disks will contain the eigenvalues. That's what the theorem says. So this is a real nice kind of graphical way of finding eigenvalues, or at least finding where to look for them.
What determines the radius of them?
Well, that's the question. So I could tell that we were having trouble getting this definition down. The radius is, what's that say? It's a sum of a bunch of absolute values. Okay? And it depends what row you're in. Row I. So disk I will be a circle. It says the distance is less than or equal to something. And this AII, what's that mean? That means that's a diagonal entry. So this is the distance from that diagonal entry is less than or equal to some number. But like you said, what's the radius? The radius is the sum of the absolute values of those those off diagonal entries, okay? Now, for this example, well, let's do it. Here's MATLAB. Let's run Gersh of A. Does it work? Well, it did something. There it is. Okay. So that's the Gershgorin circle for A. Where is it centered? 3, 0. Okay? And actually, one thing you should know about this plot, when we say 3, 0, you have to understand that this is the complex plane. Because eigenvalues can be imaginary, right? Or complex. So the real number line is the x-axis. Okay? So if the eigenvalues are real, I guess, oh, and what's the radius for this problem? The radius is, well, it looks to me like the diameter's 2, the radius is 1. But let me just make sure that you understand that from the quiz. See, it says that the diameter, or it says that the radius should be the sum of the off diagonal entries. I guess it's kind of dumb with a 2 by 2 matrix, right? Because if I'm talking about this circle, the center is 3, and the radius is right here. So that's why it's a radius of 1. Maybe a better example would be my favorite matrix. Let's do that. Let's plot the Gershgorin disks for my favorite matrix. So how do I do that? Well, I turn off this one. Go back to MATLAB. Wow, why do MATLAB? I should have you guys do this. So could everyone turn on their computer? We have a little applet there today. I don't know. Let me see. That's a great question. What the heck is it called? What they're trying to say with the notation here is add all the entries that are not where I equals j. Add everything except for what's on the diagonal, and that'll give you the radius.
You said the y value is the complex numbers?
Yeah, so z equals x plus iy. Yeah. So when I graph these things, that's right. You might sometimes get complex eigenvalues.
So but when you head it up there, shouldn't the y-axis be labeled then? Be labeled like I, negative I?
Yeah, you're right. Matter of fact, so like I had my picture up here of MATLAB, right? Let me go back to that. Here, I'll run it again. And so you're right. But I guess everybody that uses MATLAB knows this is the imaginary axis in the y direction.
Oh.
Okay? I mean, that's just standard. If you're finding eigenvalues, you should know that's what the graph looks like.
No. But what I'm saying is the numbers they chose, how come they aren't I?
Oh, that's what I'm saying. That's kind of, everybody knows that. Everybody knows that if you're graphing eigenvalues, that the y direction is the imaginary axis.
Oh, okay.
Okay?
So what, they just put real number values to it, or?
Well, yeah. I mean, I guess what to say is that here's 1i. Here's negative 1i. Here's 0.2i.
Oh, okay.
That's the imaginary number line.
I see.
Okay? So really, this point right here, if I click on it, it lets me do it. How do I do that? I select it with this thing maybe? Oh, okay, so there's a value. And I can see these values? 3.56 minus 0.823i. That's this one right here.
Gotcha.
Okay? I mean, it really is plotting points that are complex numbers. Okay? That's a good question. Now, yeah, I didn't show you how it does that, that's for sure. But I did tell you what the theorem says, at least. The theorem says that the eigenvalues have to show up one at a time in each of these disks. So my next question is, did you guys find this applet? Is it working? Hey, I can see why they said use technology on this group work. Because check out the eigenvalues. I mean, I don't know if you tried to do it by hand. I hope not. So the eigenvalues of A, according to what I have here, are negative 3.619, 1.6008, and 5.3611. Okay? So when I go to plot those, remember that what you really have here, this is the real number line, the x. So I want to go to negative 3.6, I'll call that lambda 1. And then 1.6008, I'll call that lambda 2. That's right here. And then lambda 3, we're saying is 5.3 or so. That's around here.
So those are our subjects?
What's that?
Are those your centers?
I didn't hear you, Laura.
Are those our subjects?
No, those are not the centers. Those are not the centers. Those are the eigenvalues. What's that?
What's not the centers?
What I just plotted are not the centers.
Oh, okay.
I plotted the 3 eigenvalues. Actually, the centers we ought to be able to get very quickly. What are the centers?
2, 5, and 4.
All right, let me try that then. So 2 is a center, 5 is a center, and negative 1 is a center? All right, let me do that.
4.
Here's a center of 2. Hey, what's the radius of this one? 1. Okay, so that would look kind of like this. Or so. And then 5. Okay, well that's this center. What's the radius? 3. So that goes like to 2. And it goes to 8. So this one's a bigger circle. And then, what's the last one? Negative 4. And the radius is 1. So sure enough, because I did number 2 for you guys, we verified the theorem. The eigenvalues are contained in those Gershgorin disks. But what about that second question in problem 1? It says, from this picture alone, can you tell whether or not the matrix is singular? What's that mean, singular? Oh, you guys don't know what singular means. Okay. So a non-singular matrix has an inverse. So a singular matrix doesn't have an inverse. So name 20 other things that would tell you you have a singular matrix. Okay, name one other thing. What? The rank is not equal to n. Sure. That would say it's singular. Give me another characterization. If the determinant is... Okay, let me go through it. If the determinant is not 0, that would mean it is non-singular. If the determinant is 0, it is singular. Okay, but that's not their question. Their question was, hey, if you do Gersh of A, here's the picture, right? I don't see the eigenvalues here.
You don't?
Oh, actually, I do. They plotted them. Well, pretend I don't. You didn't when you drew it, right? Your picture was here. You only had the red. Could we tell if it's singular or not?
Yeah. Because it doesn't have 0 in the value.
Right. That's the point. Already I know it's non-singular. Already I know it has an inverse because of the Gershgorin disks. You guys with me? Because 0 is not contained. Now what about my favorite matrix? Did you guys do that one? If you try my favorite matrix and do it, the Gershgorin disks are going to contain 0. And sure enough, 0 is an eigenvalue of my favorite matrix.
So you can't tell, you would not be able to tell that a matrix is not singular.
Right.
You could tell that it is. Did I get that backwards?
I think we have it backwards. Can I tell whether or not this matrix is singular? I know that this one is non-singular,
Oh, yeah.
but I won't be able to tell if it's singular. Right. Right. Then it says repeat the previous 3 questions for B. Do you guys need more time on that? Yeah?
Did you get the eigenvalues?
Oh, you want the eigenvalues? Well, we're supposed to do that at the end, right? So,
Repeat the previous 3 questions.
right. So question 1 is draw the disks. Question 2 is compute the eigenvalues and then add them. All right. So tell me when you're ready for eigenvalues and I'll punch them up. Oh, I already did those, didn't I? Here they are. 2.8 plus 0.1469i? Holy moly.
Now, on this, we consider I as like 1, right?
So I, yeah, it means in the y direction. It's like 1, yeah. So
Okay.
so it basically is telling me that my x coordinate is 2.87 and my y coordinate is 0.14. So here's lambda 1. From what I'm seeing, it's like right there. You guys see that? Oops, I just got rid of it. There's lambda 1. 2.87 and then 0.14. Now lambda 2, it says, is 0.7 and negative 1.28. What the heck is that? Well, here's 0.7 and here's negative 1.28. So here's lambda 2. And then lambda 3 is 0.4199, comma 1.13. So that's this one. Something like that. All right, so now I have to do the disks. Who needs more time on the disks? Let me ask that. Still need more time. All right, I'll pause for a minute. Here, let me go ahead and plot I'll do the last circle. The center is 1 minus I. So I go 1 in the real direction and negative 1 in the minus direction, in the imaginary direction. So there's the center. And what's the radius of the last disk? Well, it's 1. So I guess the last disk would be this one. And notice it contains lambda 2. Yeah, Trent.
So, because this doesn't include 0, now we can just be able to say it's singular, or is there more testing to go on?
Okay, so you're saying, once again, it doesn't include 0?
No, it does.
Oh, it does include 0.
So I'm just wondering
Then we
if
don't
I
know.
say it's singular, if I have to do further testing for it.
No, we can't say it's singular. As a matter of fact, this one is not singular. Because remember, to be singular, you have to have an eigenvalue of 0. And my 3 eigenvalues are not 0. So it's almost like problem 1, I can conclude that it's non-singular. Problem 2, singular or non-singular, we don't know until we compute the eigenvalues. Okay?
And then, so one of your eigenvalues would have to equal
Yeah,
0.
yeah.
Okay.
Singular means you have a 0 eigenvalue. That's one way to say it.
Okay.
Okay?
If it's singular, is
Yep.
it diagonalizable?
That's a good question. And the answer is, we don't know. Okay? Singular tells me all kinds of stuff. It means that, hey, none of those things work in the fundamental theorem of the matrices. But it doesn't tell me if it's diagonalizable or not. That has to do with multiplicities. Yeah, that's a good question. Let me finish up. I didn't do the Gershgorin disks for B. I want to do that. You guys have those. And let's see what the picture looks like. Oh, is this what you guys got? Something like this? So that one disk is really big compared to the others. And it actually contains the others. Okay? So, again, I guess what we would know is that the eigenvalues of this matrix are contained in here. Okay? Now, I mentioned that next week I'm going to be giving you guys a talk on my research, and the title of the paper that we wrote the following summer, so actually summer of 2008 we published this. It's called Eigenvalue Inclusion Regions. So now you've seen what those look like. From inverses of, from shifted inverses of matrices, basically. So if I can explain what that shifted inverse power method is, then you kind of have the story. The only thing that we don't have, though, is kind of which eigenvalue inclusion regions are we talking about. Here's one of them. It's called the Gershgorin disks. Some of you discovered on the applet these other ones called the ovals of Cassini. Okay? Just a tiny bit more complicated of a definition. But I also don't really want to go there now. If you want to look at it yourself, you can. Okay? It's all how to wisely use the time is the real battle here. I'm already at 10:45. I think you guys learned some things, and you can play with this more on your own. I wanted to go back because we were in the middle of a proof last time, and I said I better clean it up. So why don't I do that, get that done, and then after break, we can spend time on the power method, shifted it, and all these things. We can talk about the rest of the section. Does that sound good? All right. So what the heck were we trying to prove? Get the whole hover cam back up here. I think the theorem...
The 20 to the 100th power?
That's a good question. I don't know. I know you can push MATLAB, and it'll respond very well. I also know that if you ask it to do that many things, it won't finish before we're done with class.
Oh, okay.
Or maybe before we're done living.
Punch through, or?
Yeah, I mean, it goes pretty well. Trent, you had something to say. Go ahead.
Yeah, is this something that we can write in our calculator?
I'm going to say don't. I don't think it's worth it to put the power method on your calculator.
I already did.
You did?
Yeah.
You wrote it in there?
I found it online.
Oh, you found it online?
Yeah.
Okay. Well, then maybe. Sure. I mean, here's the thing. Well, okay. Let's go to the chapter for a second. We're trying to learn about the power method. So what does the power method say? I'm going to write it a little bit differently than the book. I find that this is okay, but it's pretty technical. I like this better, the theorem that it's based on, but I'm going to write it slightly differently. Okay? So let me see if I can help you guys understand this. To me, when I say the power method, here I go. So theorem. Let A be an n by n. There's Chad's favorite word. Diagonalizable matrix. Laura likes it too, I noticed. With, oh, we know what this means, don't we? With dominant eigenvalue, oh wait, shorthand, EW, with dominant eigenvalue lambda 1. So lambda 1 is somehow the biggest eigenvalue, biggest in absolute value. Okay. Then there exists a non-zero vector x naught such that, and here's how I'm going to write this, limit as n approaches infinity, should I use n? No, I already used n. How about limit as k approaches infinity, of a to the k power times x, x naught I mean, equals y, where y is the eigenvector, using Chad's notation, corresponding to lambda 1.
Can we erase that?
What's that?
Can we erase this?
Yeah. So, I find that the book, when they write it, it might be hard to see why it's called the power method. But if you look at what I wrote, do you see why it's called the power method? We're taking powers of A, in a way. Only I told you this once before. You don't ever want to take powers of a big matrix. Taking A to the 4th power, imagine you had to compute that by hand. That's a pain. And so, what the book shows you is how it's done. First we compute x1. We remember that that's a times x naught. And when we want to do x2, we don't compute a squared. We just do a times what that x1 was. You always do matrix times vector, not matrix times matrix. Save yourself a lot of work. So this tells you how it's implemented. This tells you why it's called the power method. And the theorem says that, oh, if you do this enough, you're going to find the eigenvector corresponding to the dominant eigenvalue. Then how do you find the eigenvalue? Well, what you do is this. Do a times y. If that's really an eigenvector, what's it going to equal?
Lambda 1.
Lambda 1 times y, and then you'll know what lambda 1 is. Are you with me? So that's the game.
I'd like to see an example, like a
Yeah, me too.
example of that.
And the book does really nice examples. I mean, they do. With pictures. Oh yeah, that's why I did 1, 1, 2, 0. Approximate the dominant eigenvector using this theorem. So they keep multiplying by A over and over again. And they get a table. And my software will also give you this table.
What's R and L?
Well, that's a good question. Did anyone figure that out?
R is the ratio.
R is a ratio of x to y. X to y. And what they're showing you on the picture, they're showing you these eigenvectors, but notice something. See how the eigenvectors keep getting bigger? That's a problem. It's not a problem in the sense that as long as I compute the ratio, I can see that the ratios are getting closer and closer to what number? 1. But it is a problem in the following way. If I keep doing this, can you imagine it wouldn't take a computer too long to have that be like 10,000, 9,999?
Yeah.
Or millions? Okay. And you've heard of rounding error. If I am off of x3 by 1, by just a little bit, it'll look like that instead of what it looks like. But do that with a really long vector, and a slight change in the direction is an enormous change in the difference of the eigenvector. Do you guys see that? No. Let me show you.
Your vectors are going to get way stretched out.
That's right. Let me show you the difference. Here. Here's an eigenvector. Let me make a mistake. Doot. That's a mistake. Now, here's an eigenvector. Let me make the same mistake. Doot. it's much more pronounced when the eigenvector is long.
But I'm confused because if you talk about a million and a million plus one, those are much more closer together than, say, 43 and 42. So the difference is going to be minute.
Yeah, I guess it depends where the error happens. Does it happen out there or does it happen in here? Okay. You're right. A small change out there is minute in here. But a small change in here is immense out there.
Yes.
That's what I'm saying.
Okay.
Okay.
So the smaller ones, okay, but you're saying it's
Well,
the big ones you have to worry about it.
I guess what I'm saying is we're going to do something that's very typical. We're going to scale the vectors. You notice how MATLAB, when it computes eigenvectors, always makes them unit eigenvectors? Maybe now you understand why. Because we don't want that huge chance of an error happening. And so when you look on the next page, you'll notice that they have two different things going on here. The x's are the vectors. The y's are, well, let's divide by whatever the biggest number is. So if we divide by 3/2, we get 2/3, for instance. These are not unit eigenvectors, but this is a way of scaling so that you keep it fairly small. The larger entry will be 1, and the smaller entry will be a fraction. Okay, see that? So that might tell you why we did the r's. Now you asked about L's, okay?
Ratio between if you're at K, then it's K and K minus 1.
Right, it's from one step to the next. How much has it changed? And here, now we might be able to understand the process, I think, okay? Start with some initial vector whose largest component is 1. Repeat these steps over and over again. And again, this is where I think doing a proof by induction kind of prepares you for computer programming and vice versa. Okay? Compute xk, which is a times yk. Notice, we're not going to multiply a times the big vector. We're going to do a times the one whose maximum value is 1. Then let mk be the component of xk with largest absolute value. And that's what you divide by. So what happens is when I do a times 1.91, I get 1.91 comma 2. That's my m. So I divide by 2, and I get this. And what I did was I tried to program that into MATLAB for you. Let's see where we're at. Do I have... Well, I guess I better download. Oh, here's Power Method. Okay. So let me save this first of all. It has to be saved somewhere that I can actually get to it. Where the heck is that? Well, if I don't save it, I'm in trouble. I can't use it. Here's the current directory. Do I have any other directories? Might be under FreeMat. Nope.
Usually you can just you right-click one of those methods there.
Yep.
And say open in Windows Explorer.
I understand that. I just... Here's a temp. Is it in here?
You downloaded it?
I was about to. That'll put it in temp, I think, right?
Can't you just download it straight where you want it to go?
Yeah, but I have to know where I want it to go.
You
If
go
you
to
go
your-
back, it shows you exactly where you want to go.
I know that, but that's long to remember. You guys going to help me? All right.
Yeah.
Cool. So here we are. Oh, it's not long. Documents MATLAB? We could do that. All right, here we go. Users, P. Zachlin, Documents MATLAB. I'm showing you kind of, hey, what you're going to have to do. So here it is. No. We already have it downloaded. We just have to save it. Where the heck is it? MATLAB. Here it is. Save as. The great thing is I'm recording all this in case Josh and Ethan want to see it. So save as. Here's temp. That's where I was going to do it. But we said no. We're going to put it in. Remind me? You think up?
So Paul Zachlin.
Go to this.
It was Paul Zachlin.
Documents.
Well, it's PZ. P-Zachlin.
It was P. Zachlin? That's different.
It's go to the C drive. What you do, so this PC probably?
I don't know. Here's documents. Users?
It's the file that it was, that user file, it actually links to the document on the desktop.
On the desktop?
But if you want to find the actual folder, yeah, you're going to have to go to the C drive.
Go to this PC.
This PC, C drive. Now we're getting there. Documents. Yes?
Like, you went to skipping stuff.
I know.
User.
I like skipping steps. Oh well.
P. Zachlin.
C drive.
There it is. Down here,
Users.
P-Zachlin.
P. Zachlin.
Documents.
Here, right?
That's
MATLAB.
definitely it.
MATLAB.
Yeah,
Ooh, Dungeons and Dragons. Let's look at that.
Hey.
MATLAB. Here we go.
Those all your character sheets in there.
Oh yeah. Power method. Do I already have it? That'd be funny. No, I don't. Let's just call it power method, not power method 1. Save. All right, it's there. We're ready to run. Go to MATLAB, window. We need a matrix. A equals, well,
Already in there by default?
yeah, but don't remind me of that. 1, 2, and then what was it? No, it's 1, 1, 2, 0. So I input the matrix like this, and I need x init. X init equals, in our book, what was the initial vector?
1, 0.
I think it's 1, 0, okay. 1 semicolon 0. And then we need a k value. Looks to me like we've been doing 8 steps. If you put a semicolon, then it won't spit out the output. And now I'm ready. Power method of a comma x init comma k. Enter. Well, it did it. What the heck did it do? One thing it did is it probably an answer here probably gave me the data. Hey, that looks kind of like what we had. Okay.
I think the example was 1 by 1, wasn't it? Wasn't the answer 1, 0?
Hang on. Let me show you guys something that'll help you when you do MATLAB. I almost forgot. If I go to the editor, what I find is it's really nice to use this. Just copy this. Data equals power method, etc. and paste that into MATLAB. And then you'll have kind of a real schematic of everything it possibly uses. I hit enter, and then it'll output stuff in data. Once it runs, what happened?
You didn't hit data.
I didn't?
I don't know, data didn't ever show up.
Or is it still running? Try that again. Oh, I didn't hit it, sorry. Control V. There we go. Data equals that. So now data is the variable that has all this stuff. Okay? So I think the first two columns, well, the first column is what step I'm on. And you could label this, obviously, if you want to make it better. The next two columns, yeah, those are the XKs. Then I have the YKs. And then at the bottom here, I think I have the M's. Yeah. So it is working. Okay.
So what's your lambda? What's your eigenvalues on there?
So that's a good question. What's the dominant eigenvalue according to this?
Yeah.
2.
Oh, that's the MK.
1.9884, right?
Okay.
That's my M. My MKs will approach the dominant eigenvalue. So that's really nice. The eigenvector that I'm going towards is 1, 1.
Right.
You could see that these are approaching 1, 1. Okay? We saw that graphically also. All right. So that's the power method. So just like the power method helps you find the dominant eigenvalue, the inverse power method could help you find the least dominant eigenvalue. Now, why is that? Well, suppose I have a matrix, A, and I know that its eigenvalues are lambda equals 3, lambda equals 7, and lambda equals 1/4. What's the dominant eigenvalue of A? Lambda 1, lambda 2, or lambda 3? Lambda 2, right? So the power method could help me find that, 7. What's going to be true about A inverse? Do you know the eigenvalues of A inverse? That's it. 1/3, 1/7, and 4. So the way the inverse power method works is this. If you have the inverse and you apply the power method to that, you'll come up with that. Then take the reciprocal, and that proves that 1/4 is an eigenvalue of A. Sound nice? What's the catch? Well, okay. Actually, if it's not invertible, I'm even better. If it's not invertible, then what's an eigenvalue? 0. Okay, so that'd be even better. But if it is invertible, the problem is finding the inverse. That takes a lot of work. Might be more work to do something, more work than it's worth.
Could you just use the power method and just take the inverse of the common one? That's what it seems like happened here.
So if I use the power method on A, I'm going to come up with 7. Right? The question is, how do you find any of the other eigenvalues? That's really the question I'm asking. The inverse method is a way of finding one other eigenvalue. Now, for the shifted method, you guys needed to have understood exercise 22 from section 4.3. Did I sign that one? I think so. I just don't know how many of you did it.
I looked at it.
This is one of my favorite students' work on this problem. Okay? So I thought I'd share it with you. Actually, check that out. 2008. Her name's Molly. That's my daughter. So she and Steven showed up that day. Great story. March 25th, so they were on spring break. It's my first year here at Lakeland. And Grandma says, I'll come over and watch them. You go teach. I said, okay. Well, Grandma gets stuck on the 480 bridge. I'm never going to make it. I'm like, all right, meet me at Lakeland. So I brought them. I said, all right, Molly, Steven, take out a notes. Here's Steven notes. These are even better. They're from, I mean, he was in kindergarten at the time, all right? So, but anyways, here's Molly. She wrote it down. So evidently we didn't have the Chad arrowhead yet on eigenvector. But here's the theorem. If V is an eigenvector of A, and the eigenvalue is lambda, then V is also an eigenvector of A minus CI. So that was the exercise. Same eigenvector, but different what? Different eigenvalue. It's going to be lambda minus C. So the eigenvectors stay the same, and then they had asked me how to do it, so I did it in class, and evidently, well, maybe I should give you guys different notes. That's funny. Oh, here's the thing about smallest eigenvalue. That's what we were just talking about. And then, putting these two methods together, we get the shifted inverse power method. So you can see it's not that hard. No, that's funny. We're out of time. I guess next time I could talk a little bit more about shifted inverse power method. On Blackboard, there is another file that might help, but I guess we got to wait till we get MATLAB, right? Okay. Well, do the best you can without it. And anyways, hope you had fun today.
So were you going with that point that it's faster?